Good morning everyone, and thank you all for being here. Today I got the opportunity to present to you my paper with the title, as we already heard, Evaluating the Angular Resolution of a Simulated Light Field Display in Regards to Three-Dimensionality, Motion Parallax and Viewing Experience. Since the title might seem quite long to all of you, I will lead you into the topic and tell you exactly what we did. By now, probably most of you have seen digital advertisements like these, where huge LED walls show a kind of digital room extension into the back. And as we can see, it looks amazing from this perspective. It looks really three-dimensional, but it changes as we move around and look at it from a different point of view. We will then face major perspective problems, as we can see, because we always see the same image no matter where we stand. I will quickly give you an introduction into some display technologies to take us all to the same starting point. And we all know conventional 2D displays, just like my computer monitor right here. And if I move around in front of it, I always see the same image like a normal display. But there are different displays that are capable of showing more than just one source image. So they cast different images into different directions in space. And if the viewer moves around in front of it, we can see different images according to their position. And if we would fill all these views with with different views on the same scene, we can actually simulate a motion parallax. And that means that we will gather different information about the scene as we move around in front of it, because we will always see a different image. And by using and adjusting this mechanic, we can actually simulate a kind of light field display with a working motion parallax. And if we would use a stereoscopic 3D display, also we can simulate a stereo parallax, but in this particular study I'm talking about right now, we used a standard 2D monitor and we just evaluated the effects of the motion parallax. So a light field display shows several views of a scene, and for our study we created 7 different stimuli with a different range of angular resolutions. But what exactly does the angular resolution affect in the displayed image? So here we can see 2 different examples with different angular resolutions. The top one with the orange, red and yellow is rather high with 60 degrees per view, while the bottom one is lower with only 10 degrees per view. And the resolution is calculated by the field of view of the display to its number of views it displays. And on the top right, we can see the views displayed in a top-down view, and we notice that the more views we have, the closer the views are actually together, and the more similar is the information about the scene. So we can see it in the 2 right images. And we can also see that we have visible vertical slices in the top image, so we can very clearly see that we have red, then orange, and then yellow. But the bottom one looks much smoother. It looks almost like a gradient. Since the different views become more similar to one another. And the same effect will apply to light field displays with lots of displayed views. The more views we have, the less different are the views and the less vertical artifacts we will have. And just as a side note, for our study, we only simulated the horizontal motion parallax, which means moving left to right and front to back in front of the display, since people normally don't change in height when they move around, and we had to save some render power. So, in relation to the angular resolution, there were 3 factors we wanted to survey. How does the effect of the three-dimensionality changes? Does the motion parallax help to recognize the shape of the displayed object? And does it even improve the viewing pleasantness? And with that said, the questions we asked were: how three-dimensional does the object appear? Does the position-dependent appearance of the object help to recognize the shape? And how pleasant is the viewing experience? Here you can see a final stimulus of the study. I thought I would show it right away so we can all imagine what we are working towards with the presentation right now. And what happens is that the conventional 2D monitor, so this is just a very basic computer monitor, simulates the light field display, and depending on the person's position in the room, each pixel shows a specific predefined color. So most light field displays are built using subpixels, as we can see here. So every pixel has a number of subpixels. In this example, we have 3 different. We have blue, yellow, and red. And we have a lens that leads the light of the subpixels into specific directions. So here we can see that the blue subpixel would be seen from the left, the yellow one from the front, and the red one from the right. We applied a specific emission pattern to each of the subpixels with a linear fall-off. And what we get now is that the sum of light intensities is always at 100%, like all around the pixel. And this is good since we have no loss of luminance, but at the same time the pictures blend into one another. So for example, in the left image, if we look at the 30-degree angle, we would see 100% light intensity of the blue subpixel. At 60% we would have 50% of blue, 50% of yellow, and at 90% we would have full yellow, and that continues all around the display. And with that information we can now actually create the simulation. So we quickly go back to the stimulus, and we now understand that we are working with subpixels and their viewing angle dependent visibility. And the next step is to actually calculate the visibilities of each subpixel we want to display. And this is done by tracking the person's position. We can actually see the Xbox Kinect right underneath the monitor, and there's a picture of it. It's just a black box. And we track the head of the person in space. When we obtain their position, we can calculate the viewing angle based on that. And therefore, we can calculate the intensity maps, or in a more technical sense, the alpha maps. And these will later get combined with the source images that we will render in Cinema 4D, but to show it right here, it's still just blue, yellow, and red. So basically, we apply the alpha maps from the middle to the source images, and we add them all up, and that gives us the final displayed image. And to generate these alpha maps I just showed, we have to find out the exact viewing angle from the user onto each and every display pixel. And like I said, we track the position of the person in the room, and through a rather basic trinomial calculation, we can obtain the viewing angle delta, you can see here in red. And we only have to do one case differentiation. So if the person is on the left of the pixel, we just calculate 180 degrees minus the arcus tangens, and if the person is on the right, we just take the arcus tangens, and that's how we can generate the alpha maps. Down below you can see on the left again the color values of the subpixel, and on the right we can see one display line and the corresponding alpha map to it. In the next step, we need to render the source images in Cinema 4D, just as I said, because we don't want them to be just solid colors. And the stimuli show a minimalistic object consisting out of basic geometric shapes that are interwaved so that occlusions occur. Moreover, it is shifted by 45 degrees to provoke lots of diagonal lines, since these diagonal lines are very visible in the vertical stripy artifacts I just explained at the beginning. We can imagine that if we have just horizontal and vertical lines and we would have an artifact like sliding through it, we wouldn't really see it, but if it's a diagonal, we get kind of an offset, and it looks very unpleasant. And it floats in a minimalistic space that extends to the back, and it's rendered in Cinema 4D. You can actually see in the video the render cam that just slides around it in a half circle, and any horizontal compression that occurs is corrected by in-camera distortion maps. The stimuli were evaluated by a study amongst 32 participants, of which 18 were male and 14 were female, and the average age was 24.9 years. And it was a quantitative survey to survey a mean opinion score that ranges from 1 bad to 5 excellent, so it was a subjective rating. And we determined the mean opinion score for 7 different numbers of views. The first one only had 1, so it's basically a normal display, and the other ones were 6 simulated LFDs with 45 views, 90, 180, 360, 720, and the highest one had 1,440 views. The subjects would enter a room with a masked area on the floor in which they can move freely, but they are instructed to move from each outer corner at least once per stimuli. And the simulated LFD is installed at eye level, and it has a size of 32 inches. In the beginning, there is a short training phase in which the 45 views and the 1,440 views example are shown to guide as reference. And if we take a look at the left video, we can see some weird ghosting going on, and it looks kind of laggy. And the right video looks much more smoother. We can't see any ghosting. Yeah, and these were the two stimuli the people saw in the beginning to kind of calibrate their understanding of what they are looking at. And after this training phase, all 7 stimuli are presented in random order per person. And now onto the results we gathered. The first question examines a subjective rating on how real the presented object behaves in comparison to the real-world surroundings. It is neither about the quality of rendering nor the effectiveness of the simulated motion parallax, but overall on the appearance and of the feeling of the object and the setup. And we can immediately see that the ratings rise with a higher number of views, and we almost have a linear rise in MOS by a logarithmic rise of views. So we notice that on the x-axis we have a logarithmic scale, and on the y-axis we have a linear scale. And that means that doubling the presented views always results in a similar rise in MOS. So it doesn't matter if we only add 45 views or if we add 360 views, we always get the same kind of rise in the mean opinion score. And we can see that the largest increase in MOS can be found between 180 views and 360 views, while the smallest increase is located at the very top between 720 views and 1,440 views. At the same time, we have the second largest standard deviation at 720 views and the smallest one at 1,440 views. And this could indicate that the probants were more confident in giving the lowest angular resolution a good score than they were with the 720 view stimuli. For the next question, the subjects should focus on the motion parallax, and they should evaluate by standing still versus moving if they gain more information about the object shape. And again, the ratings show a nearly linear rise in MOS between 45 and 720 views. We can see a plateau and even a slight decline forming between the top ones. And this indicates that the participants might not have recognized the difference between these two stimuli, since objectively the higher number of views offer less artifacts and therefore more information about the shape. But in ratings we can't see such an increase, so it's questionable whether they really recognize the difference between these two stimuli. And the last question is subjective and emotional as well, since even an artifact-free image is worthless when it's unpleasant to look at. The one view rating stands out here since the participants agreed in rating it decently with about 3 points on average, which is greater than the ratings of 45 views, 90 views and 180 views. But at the same time, we can see that the ratings fluctuated a lot because we have a very high standard deviation at this point. The largest increase in MOS is located between 180 and 360 views again. So this step seems to enhance the experience a lot. And the 1,440 views stimuli still got the highest MOS and also the smallest standard deviation. So participants agree that this should be the most pleasant stimulus. And when comparing this observation we have right here to the ratings of the other two questions I just showed, it seems kind of odd, since in the other two questions they always rated the 720 and 1,440 views stimuli almost the same. But here we can clearly see that they prefer the lowest angular resolution. So we ask ourselves, do they recognize a difference? Because they don't seem to gain more information about the shape, but they still kind of like it better. So what are the conclusions we can draw? Overall, the MOS rises with a higher number of views. And we can see that the effect of three-dimensionality and the recognition of shape is better with the LFD than with the one-view example. But in contrast to that, we can see that the one-view tops 3 out of 6 LFD stimuli in regards to the viewing pleasantness. The plateau can be seen at the first two questions, but not at the third, since we still can see a rise. But we also have to admit that we have a significant standard deviation throughout all of the questions we asked. And this is due to a number of reasons I will show you right now in the limitations. Overall, as I said, the metrics are very noisy. We have an average standard deviation that ranges from 1.74 points to 1.8 points, which is rather high when we look at the fact that the scale is only from 1 to 4 points. And this could be due to a number of reasons we could see here. For example, the low sample size of very few participants, different movement patterns in space, maybe we have to track that. We have some biases maybe, for example, the shape of the object. Maybe if we choose a different shape or a different challenge, it would be different. maybe we have a learning effect from the shape. Maybe we have to, randomly assign each shape to each stimulus. And then we also came up with some ideas for future work to even lower the angular resolution, to examine that, and to lower the step sizes between the resolutions to verify maybe a plateau or find different results. Yeah, and that's it. I thank you all very much for listening, and feel free to ask me anything or reach out to me here in person or via my contact details.
Yeah, thanks a lot, Sophie.